So the first thing is that we have a complete learning of the Newman projection, and also we showed you how to calculate the energy cost of different conformers using the Newman projection. And also we introduced some different types of strings, including the torsional, angle, and steric strings, and their definitions and their applications. Okay. Also, we learned the strings, the type of strings, and how much the strings are in cycloalkanes, and we have a slight touch of the conformation of cyclohexanes. Okay, there are also several things I need you to do and to keep in mind. So one of you actually asked me so whether I can share the 3D app I used during the teaching, right? So the bad thing is that this is a licensed software, but the good news is that I found you a website that can do almost the same thing. So you can actually visit the moreview.org, okay? And let me show you here. So basically, it's a simplified version of the software I have used during the presentation. So for example, if you draw a 6 numbering and you click 2D to 3D, okay, and the website can show you the 3D structures. You can use your mouse to rotate it, and you can see a different bonds, and you can see from different directions, and you can change it. You can see, let's see, 5 numbering. You can also see the complements, different complements. You can see the 4 atoms are in a plane, and they kick this atom out of the plane. So this is an envelope-shaped molecule. Okay, so keep this website in mind. So if you don't have a model at hand and you want to quickly know the structure of a molecule, you can go to this website. All right, the second thing is that the nomenclature drill is open now, so you can go there and attempt the 10 questions in there. You can attempt as many times as you want, okay? And also, several of you haven't signed up for the tutorial. Hope you can sign them up. And if you have any questions, contact the tutor, okay? Let me see how can I. All right. So another thing I want to talk about before we start class today is that one of you asked very good questions about nomenclatures, and I want to explain it a little bit. So in Professor Chew's video, so when you are encountering those kind of multi-substituent alkanes, right, for the naming, so with more than one substituent, so the parent chain is numbered in the direction that has the lowest numbers in the name. Okay, so this is a bit confusing for some of you. For example, so what does the lowest numbers mean, right? So for example, in Professor Chew's slides, so she showed this molecule, which is named 1-chloro-6,6-dimethyl, right? So basically, they put the chloro at 1 and the dimethyl at 6. Okay, so there are 2 ways to name this molecule. One is that, like Professor Chew showed, 166. The other one is 227. So you put the methyl at 2, right? So some of you told me that they think this should be the right one because the 4 plus 7 is 11. That's lower than 13, right? But I want to explain that because so when you compare these numbers, you compare the number from the smallest one by one. So you don't compare the sum of it. You compare that the lowest one in this group is 1. The lowest one in this group is 2. Because 1 is smaller than 2. Sorry, this is a typo. Okay, because 1 is smaller than 2, so 166 should be the right one. So you can't name this 7-chloro-2,2-dimethyl because you have to name it with the lowest number in all of these numbers, which is 1. All right. So I hope this is clear. So last time, at the end of the last lecture, so we have a slight touch of the conformation of cyclohexane. Okay. We show you that it is not a plane structure, and it is the most comfortable conformation. It's called a chair conformation, so shown here, and it's like this chair in this ugly picture. And also we show you that it is very comfortable with the conformation and all bonds are staggered. So it has zero strain energies in it. And we also show you, I also show you that how to draw these cyclohexane chair conformations. So, basically you need to follow these, you are recommended to follow these steps and draw a beautiful conformation of chairs of cyclohexane. And I also show you that I have uploaded a practice sheet on Moodle, so you can print it and practice on yourself. Okay. And so let's start this lecture by a detailed information about this chair conformation. So actually, the chair conformation has a ring equator and an axis, just like our Earth. Okay, we have an equator and we have an axis going through North Pole to South Pole, right? And what does that mean? So if we have this ring equator, we can classify all these hydrogen substitutions. So axial CH bonds, like shown in blue, is actually perpendicular and pointing above and below the equatorial plane. So this is 90 degrees above the plane. This is 90 degrees below the plane. And there's another type of CH bond, which is called equatorial. So it's derived from equator. Okay, so the equatorial CH bonds are almost parallel, but they are directional. Okay, and they radiated from the ring. So it's like like a rocket going out of the Earth. Okay, it's going back, left, right, front. All right. Okay, it's easier to explain it with a model. So this is the model of cyclohexane in its chair conformation. So you can see the blue one, like here, axial CH bond. The red one are equatorial. So let me open this model for you. So if you move with this model, you can see the 6 carbon form some kinds of like a plane, right? And then this blue bond are perpendicular and they are parallel to each other. And for the red one, it's like a ring. It's radiated from the ring. So it's like pointing almost parallel to the plane, but it has some angle. You can see this is pointing up, and this is pointing down. All right. So if you look in the direction that above the plane, you can see the blue one, the axial CH bond, are actually pointing to you, right? And the red one is pointing out, and this is a different angle. So you can see I also show the different angles here. So let's summarize those kind of axial and equatorial positions. So cyclohexane, the chair conformation, has 6 equatorial protons on the equator of the ring. 3 facing down, 3 facing up. But notice it's slightly, okay? It's not like the blue one, which is 90 degrees. It is slightly above, slightly below, slightly above, okay? It also has 6 axial protons on the equator of the ring, like 3 facing down, 3 facing up, but this is perpendicularly, so very drastic change. All right, and because this equator and this planar ring, so we have different faces of the cyclohexane chair conformers. So one is what we call top face, the other one is bottom face. So each carbon atom in the chair, like this one, has one axial. In this, for example, this one is pointing down, and the one equatorial in this one is pointing slightly up. So for each carbon, it has one proton down, one proton up. Okay, but for each face of the chair conformation, it has 3 axial and 3 equatorial. So, and in alternating arrangement, for example, for in the top face, this 3 axial, right? And you have 1, 2, 3, 1, 2, 3 equatorial. They are like in a alternating arrangement. For example, this pointing up and this axial pointing down, this axial pointing up, this axial pointing down. Okay, just keep these information in mind. And because of this ring And because of the plane of the chair conformation, we now have the cis-trans stereoisomers, just like we talked about in 3-membrane and 4-membrane. Okay, so again, if you recall, the cis stereoisomer has the same substituents on the same phase. Oh, sorry, has substituents on the same phase. Okay, this thing is abundant. So for example, so we have top phase, bottom phase, and for this cis 1,2-dimethyl cyclohexane, you have this methyl group pointing up, right? And another methyl group also pointing up. But if you have a trans 1,4-dimethyl cyclohexane, so this methyl is pointing down, while the other substituent, the methyl, is pointing up. So because there is an imaginary plane, so if they are on the different phase, this is on the top phase, this is on the bottom phase. So they are named trans instead of cis. Okay. And another thing I want to talk with you is that sometimes we draw chair conformations with bold bonds. So if you remember when we draw the sp3 carbons, we have the bold bond, meaning that the bold bond is pointing out of the plane to you, right? And the dashed bond is pointing away from you. So the same applies with the chair conformations. So if we draw chair conformations like these two, so you should be able to realize that this bold bonds are actually pointing to you, which is that these bonds are in the front and these bonds are in the back. Okay, the same applies with this. So these 3 bonds are pointing kind of to you, and all these non-bold bonds are actually in the back of the molecule. So you can have a 3D feeling of the chair conformation. So here I need you to practice with me. So maybe some of you have already practiced on drawing the chair conformations, but I will practice with you this time on drawing the chair conformations of the cis 2-methyl cyclohexane 1-ol. So to draw this, you first need to realize to figure out what's the structures of this, right? And so draw it you here. Okay, here. So first, if you are pretty new to this, you don't need to draw the chair conformation directly. Okay, you can just see what's the structure of this. Okay, you can see this is a 6-membrane cyclohexane, right? And it has a cis conformation with 1 methyl and it's an alcohol. All right, 2 methyl. Let's see if 2 methyl pointing up, and 1-ol. 1-ol is also pointing up because it's a cis conformation, right? All right, so we have the feeling of the structure now, and then we draw, just follow the steps of drawing a chair conformation. Draw a chair first. So 2 parallel lines, and then past each other a bit. All right, we have a chair. Again, I draw kind of ugly because I'm using Apple Pencil, so I'm drawing pretty good with the normal pencil. Okay. Then if we have a ring structure, we put substituent on it first. Okay. So now we have a OH that's pointing up. All right. So let's see. So for this carbon, the pointing up is an axial OH. Okay. And then we move to the next carbon with the methyl group. It's also pointing up. But remember, they are alternating, right? So this methyl, when pointing up, should be an equatorial. So we have a methyl pointing up. Huh, pretty good. All right. And then because I asked you to draw all the hydrogens, so we can just draw all the hydrogens here. And we have axial, we have equatorial, axial, equatorial, equatorial, axial, and axial. All right. So this is a 1 chair conformation of the molecule. And to draw another one, also I have prepared this in the practice sheet. There is another type, which is kind of like the mirror image, okay? You draw these 2 parallel bonds first. All right, and then you draw this one first, okay? This one. Okay, so now let's put the alcohol on the equatorial first, which is let's see, the alcohol is pointing up, right? So let's try this carbon. So the alcohol, if it's pointing up, it's up like this, right? And the hydrogen is pointing down. Okay, the methyl next to it, now it's also pointing up, but in this time, the methyl becomes axial, which is in this carbon. So let's put the methyl here. All right, and we can also make all these other hydrogens appear. Hydrogen, hydrogen, hydrogen. See, you have two chair conformers of the cis 2-methyl cyclohexene 1-ol. All right. Okay, let's go back to the slides. So now we have learned to draw the two chair conformations, right? And now let's move to figure out what's actually, is there any relationship between these two types of chair conformation. So I marked these numbers here. So this is carbon 1, 2, 3, 4, 5, 6. Okay, and another one I marked as 1, 2, 3, 4, 5, 6. So that I mark it this way because that they are related. Okay, this carbon, when it goes through a process called ring flip, it moves here. All right, when carbon 6 goes through a process called ring flip, it's bending down to carbon 6 here. Okay, and it's kind of like 6 moved to here, 1 moved to here, and all the other carbons just moved in the same way. Okay, so what happened? So what changes between these two conformations after what we call the ring flip? The net result of the ring flip has 4 consequences. First, on the left one, the blue hydrogens are equatorial, like the C6 hydrogens equatorial. And on the right, on the C6, the hydrogen is pointing down. It's axial now. It's not equatorial, okay? And the red hydrogens from axial, it's now equatorial. Carbon 1, axial pointing down. Carbon 1, the pointing down, but now it's equatorial. And the C2, C4, C6, it's above the equator, like 2, 4, 6, above the plane. And now, after you bent it and the ring flip it, like 2, 4, 6, now it's below the plane. Okay, see it? And the 1, 3, 5 is the same. 1, 3, 5, at the beginning, it's below the equator. But after the ring flip, 1, 3, 5 is now above the equator. Okay? What doesn't change is that what if the hydrogen is pointing up in the original ring conformation, it's still pointing up in the finished ring conformation. So for the C6, we have an axial in C6. At the end, we also have the hydrogen becomes equatorial. But what doesn't change is that it's still pointing up, okay? But it's just pointing up from axial pointing up now becomes equatorial. All right. So you need to remember this, and I will show you how this ring flip happens, and so you can easily remember this. So how does the ring flip proceed? So it's going through two processes. So the first one is that you can imagine, so the C3 is from down to up. So we just pull this carbon up. Now the C3 is up, right? And this part of this molecule in the first step doesn't move. So both ends of the conformation is up now. It's like a boat, okay? Again, that's why we draw a very ugly boat here. So it's a boat conformation. And then after you pull the carbon 3 up, you then pull the carbon 6 down, okay? Now, exactly, it becomes the final conformations, right? So actually, I have a model to show you here. And if you can see this, I don't think you can see this clearly. Okay, okay. So you can see we have all the white CH bond in the axial position, right? And then how does it become the other conformation? Is that first we pull this carbon up. See, it becomes a boat, right? Kind of like boat. Then we pull this carbon down. All right. So this become another chair conformation, right? And then what's the difference? So now you can see at the axial position it's red, right? And the proton used to be at the axial position is here, the white one, white one, white one. It's still pointing up, but it's now in equatorial positions. All right. Let's go this again. So let's go back to the original one. So let's pull this carbon up first. Chair conformation. Okay, let's pull this carbon down. Oh no, this is the boat conformation. Then pull this carbon down. Now it's chair, right? See, the white carbon is pointing axial again. It's still pointing up, but it's pointing axially. Okay, so if you have a model, practice on this. Okay, if you know the ring flip process very clearly, it really helps you to understand a lot of stereochemistry of the chair conformations and the 6-number rings. Okay, and so you see there is a boat conformation, which is totally different from the chair conformations here, right? So let's learn more about the boat conformation. So in the boat conformation, you can see that all C3 and C6 are both up, right? And this actually creates an interaction between the CH bond of the C3 and the CH bond of the C6. So what we call here is a flagpole interaction because it's a boat, right? At the front of the boat, you have a flagpole. At the end of the boat, you have another flagpole. And if these two flagpoles are too close to each other, you have these two hydrogens closer, right? And this creates some steric strain, okay? So it's not a torsional strain because they are these carbon are not bonded, okay? You do not rotate the bond to create a strain. It's steric because they are non-bonded groups that are too close to each other. Okay, and if you look through this direction of this molecule, you can see now you can see that these C1, C2, C4, C5, all these CH bonds are eclipsed. Okay, not C3, C6, because C3, C6 is far away, but C1, C2, they are bonded. C4, C5 also bonded. So that creates torsional strain between these CH bonds because bonds are eclipsing. Okay, and so you have a steric strain between the flagpole interaction. You have a torsional strain between these eclipsing CH bonds. So actually, the strain of the boat conformation is 28 kilojoule per mole higher than chair conformation. Okay, so chair conformation is really comfortable, fully relaxed. But if you go to the boat, it's really strained. So that's why boat is exists in a very short time, and the boat only exists as the intermediate between these two limiting chair conformations. Okay, and the actual process, as I show you, is simplified to let you know easily like this, right? But the actual process is very complicated, and it goes through a half chair, which is even higher in energy than the boat conformation. And you have a twisted boat with a lower in energy than the boat. But again, for the requirement of this course, you only need to know that the two chair conformation interchange via boat conformation, which is shown here. And you need to understand what types of strings exist in the boat conformation. All right. And I have provided you here to a video link that you can see an animated model of the chair conformation, and you can see the animated model, the animation of the ring flip process. Okay, but I would suggest you to have a model, and that's the most straightforward way and the easier to understand way to have this ring flip process. All right. So so why do we care about the ring flip? Because on the left you have the CH bond, and on the right you have the CH bond. They're totally same in energy, right? Because there are equal number of them on axial position, equal number of them on the equatorial, equal number of them pointing up, and equal number of them pointing down, right? So what's the difference? So actually, there is no difference for the unsubstituted cyclohexane, but there is huge difference in the monosubstituted cyclohexane and what we are going to learn, multi-substituted cyclohexane. So if you have a cyclohexane with only a methyl group on it, so you can see if we put a methyl group on the axial position, right? After the ring flip, okay, ring flips. So the methyl group still pointing up, the carbon moves here, the still pointing up, but now the methyl group is on the equatorial position. Okay, the ring flip doesn't change the direction of the functional group that is pointing, but it changes the whether it's axial or equatorial position. Okay, and you can see from the reaction perspective, the reaction actually favors the side of the equatorial methyl. But why? So it must be something related with the energy that the equatorial methyl is more comfortable. So the thing, actually the thing we call the reason why the equatorial methyl is more comfortable is because when you have an axial methyl, the axial methyl have some interaction with the two hydrogens marked in red here. Okay, and using this space field model, which all the atom is shown in their real size. Okay, you can see this methyl group is really close to the hydrogen on this carbon and hydrogen on this carbon, which is in the axial positions. Okay, and the equatorial methyl conformation is more stable by 7.6 kilojoule per mole. All right, and so if you know the energy difference of these two conformers, you can actually calculate what's the in a mixture of them, what's the percentage. Okay, because it's understandable, right? So if this conformation is lower in energy, that means that in the mixture of them, this accounts for the majority because everyone wants relax. Okay, so there is an equation you probably already learned that linked the relationship between the equilibrium constant and the energy difference. Okay, so this is a graph that is based on the equation. So let's see. So you have 7.6, all right, 7.6 kilojoule per mole difference. You can see the less stable conformer, which is the axial methyl, right? It's about 5%, all right? And the more stable isomer, the equatorial methyl isomer, is 95%. Okay, it's easier to know that if you are given energy difference, so what's the percentage of the more stable conformers in the mixture, and what's the percentage of the less stable conformer in the mixture? So why the interaction? What is the interaction between the hydrogen and the axial methyl called? It's called a 1,3 diaxial interactions. So the 1,3 diaxial interaction is the difference in energy between axial methyl conformer and equatorial conformer because their interaction with the 3 position substitution. So this is another steric string. So just to recall, several minutes ago, we just talked about one kind of steric string because these two hydrogens are too close to each other. It's called a Blackmore interaction. Okay. For the axial, it is called 1,3 because 1,3, it's because this methyl and this hydrogen, their carbon is 1,3 to each other. And they are all, it's called a diaxial interaction because they are all on the axial position. So this one have this both axial, so they have interactions, and this one axial, this methyl axial, and these are all too close to each other to create some steric string. All right. Now we already know that 2 pairs of hydrogen methyl have a 7.6 kilojoule per mole higher energy than the totally relaxed one. So because there are 2 pairs of them, 1 pair, 2 pair. So each pair of those hydrogen methyl interaction is 3.8. And I have to remind you that each pair of the hydrogen doesn't have any 1,3 axial interaction. So we set this one as the 0 point of this energy comparison. So, okay. And because now the axial position are all hydrogens, right? Hydrogen, 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 because it's 0 energy, so they don't have any interactions, and they are quite away from each other, so they are pretty comfortable. So this is 0 kilojoule per mole. This is 7.6 kilojoule per mole because it has 2 pairs of 3.8 kilojoule per mole 1,3 diaxial interaction. Okay. This is the conclusion that in general, the chair conformation with the substituent at the equatorial position is more stable because there are no 1,3 diaxial interaction whatsoever. Okay, and here I listed some data for the 1,3 diaxial interactions, and so you can see if R equals H, so HH doesn't have a energy cost, just as I mentioned. Okay, so H fluoride has a 0.5 kilojoule per mole, and when the functional group of R increase dramatically to like a tabutyl, which has a carbon that has a 3 methyl group on it, you can see the interaction costs a lot of energy. It's almost 11.4 kilojoule per mole. Okay, and so if for methyl is 3.8, but for the tabutyl, and this one is the isopropyl, it increased, and especially for the tabutyl, increased to 11.4. And if I want you to do some energy analysis during the midterm or the final exams, these data will be provided on your midterm, okay, in the PDF of the file. Okay, so you don't need to memorize all these data. Okay, so now let's move on from the mono-substituted cyclohexane to poly-substituted cyclohexane. All right, so for the mono one, you only have to consider when the mono-substituted functional group is on the axial, right? But for the poly-substituted, it's more complicated. For example, those 1,3 disubstituted cyclohexane. So when there are 2 conformers for that, you can draw that, right? And then if it's a 1 cis 1,3, so that means if one R is on the axial, the other R is also on the axial. Now you have 1,3 diaxial interactions, not only between these 2 R, it's between this red R with H, also blue R with H, because they are all in 1,3 positions, right? But if you draw another conformers of this cis 1,3 relationship, you can see this R is on the equatorial, this R is also on the equatorial. Both of them are pointing up, so cis. But in this case, there are no 1,3 diaxial interactions. Okay, so for the cis 1,3 disubstituted cyclohexane, majority of the conformers are this because it's more comfortable, and this one is really congested around the 1,3 positions. And but for the trans one, so if this R is pointing up, so that means this R is pointing down because it's 1,3. So this is equatorial. So the 1,3 diaxial interaction now only exists between this red R and the 2 hydrogens here. So 1 pair, 2 pair. There's no 1,3 diaxial interaction between these 2 hydrogens. Okay. So then if you flip the ring, this R is still pointing up, but it's equatorial. This R is now pointing down. It's also pointing down, but now axial. Now you have a lot. You have another pairs of 1,3 diaxial interaction. So this blue R is now interacting with this H and this H. Okay. So really, for the trans 1,3 disubstituted cyclohexane, it really depends on the relative size of the red and the blue R. Okay. So it's easy to understand. So if you have a very big R, so this interaction is obviously larger than the smaller R with this 1,3 diaxial. So if you have a 1,3 disubstituted cyclohexane, you want to put the big R on the equatorial position. Okay. So how about 1,4? So the same method of analyze is that, so you have cis 1,4. So you have 1 R in the axial position, and you have another R on the equatorial. They are both pointing up. So the 1,3 diaxial is this one. So if you put the blue one on up, it's 1,3 diaxial with the blue one. So again, which one is the majority of the mixture depends on the relative size of the red R or the blue R. The 1,4 trans position. Okay. So if you put the R on the axial position and you put the blue R on the axial, you have to put blue R on the axial too, right? Very congested conformation. Okay. We have 4 pairs of 1,3 diaxial interactions. Okay. But if you put the red R on the equatorial, another R is trans to it, so it's pointing down, but also on the equatorial. So this is totally relaxed. I would say this has a very drastic energy difference between between these two chair conformations. Okay, so I talked about 1, 3 and the 1, 4. So 1, 2. So let's do the exercise together. So how about we have two compounds. The first one is the cis 1,2 dimethyl. The second one is trans 1,2 dimethyl. So if I give you all these energy difference, could you tell me which in each of them which chair conformation is the majority of the mixture? So so the solution strategy for these type of questions, if you encounter them in the final exam or midterms, is as below. So first, you should draw the skeletal structures of these cyclohexane to figure out what does it look like first. Then you draw all the chair conformations, which are 2 for each compound, right? Because you have the flip, then flip back, flip. Okay, and then you identify and all the interactions exist in each component and consider the sum of these energy costs, and you can make a decision on which one is more stable and which one is the majority of the components of a compound. All right, so we have cis 1,2 dimethyl cyclohexane, okay, and so this is the skeletal structures. So let's draw the chair conformations then. So if you put one methyl in the axial position, the neighboring methyl, because it's cis, it's also pointing up, but now it's equatorial, right? Then you flip this ring. Now this methyl is still pointing up, but it changes from the axial positions to the equatorial positions. This methyl, again, still pointing up, but it changes from the equatorial to the axial position. All right. And then with these two chair conformations, let's see the energy. All right. So for this one, let's see this we just learned 1,3 diaxial. Each methyl is 3.8. So this 1,3 diaxial interaction is 7.6. But many of you are very easy to forget that if we have a bond linked to two functional groups, we now have something we learned in the Newman projection, those torsional string. Okay, and because bonds are eclipsing or bonds are gauche to each other. That's why in the beginning I put you another chart that show you that gauche. So this is kind of like a hint that you also need to consider that gauche interaction and the eclipsing interaction. All right. So for this one, these two methyl, if you look through this direction, 60 degrees apart, they are gauche to each other, which is 3.8 kilojoule per mole. So the total energy is 7.6 plus 3.8. All right. And then if you consider this chair conformations, now the axial is between the blue methyl and the two hydrogens, 1,3, right? But it's the same. It's the 7.6 kilojoule. And also these two methyl, if you look through this direction, 60 degrees away, and dihedral angle is 60 degrees. So it's still have a gauche interaction. So the total are the same with another chair conformations. So the conclusion is that both conformers are equal in energy. So it's a 50-50 mixture of these two conformations. So let's go to the trans. So for the trans isomer, you draw the chair conformation. So if one methyl is axially up, the other methyl is axially down. Okay, you flip it. One is up, now equatorial. One is down, again, now equatorial. Okay, so for these 1, 2 with both axial, you have 4 pairs now. You have 4 pairs of 1,3 diaxial interactions. Okay, each pair is 3.8, so the total is 15.2. And do they have gauche interaction? No, because this methyl pointing up, this methyl pointing down. Their dihedral angle is 180 degrees, so they don't have any interactions based on the torsional string. So the total number is 15.2. Okay, so if you have put both of them on the equatorial position, all right, you don't have axial interactions anymore because all the axial are occupied by hydrogens, and the hydrogens do not have a 1,3 diaxial interaction with each other, 0. All right, but you have one pair of gauche interaction because the dihedral angle between this methyl and this methyl, if you look at this direction or this direction, 60 degrees. So you have 3.8. The total is also 3.8. So the conclusion is that the right conformer is in much lower energy than the left one. So because it's lower, everybody wants to be relaxed. So the majority of the mixture is this complement with both muscle on the equatorial position, one pointing up, one pointing down. So again, if there is a similar question in midterm or mid or the final exam, just analyze them using this kind of method. All right. So then we have a similar analysis that can be performed for other disubstituted cyclohexane and polysubstituted cyclohexane. But you really need to practice on them by yourselves. Okay. For example, you can go back home and see whether you can draw all the conformation, chair conformation of these four, and see what kind of strengths can you identify in these structures. And although you don't have data for these energy costs yet, but try to identify the strengths in these structures. All right. So so to finish this chapter, so we look at several other 6-membrane compounds. So that is very interesting. So this one, cyclohexane, we learned something about this. And so this is the sugar, which is glucose in its chair conformations. You can see the natural or the major conformers of the cyclic sugar is that you put all the bigger group like the OH in the equatorial position. So it's more comfortable, right? So another compound of the 6-membrane and then it also can adapt a chair conformation is acetal. So basically, it's a carbon with two oxygens, and 2 oxygen is existing in a ring of 6-membrane. So on oxygen, there is no substitution, and if there is any substitution on this carbon, the majority of the complement is to put this substituents on the equatorial position to avoid any 1,3 diaxial interactions. Okay, so another compound I want you to pay attention to is called decoline. So decoline is this compound which has the 2 6-member rings fused together with share a bond together like here. Okay, so and the bridgehead carbons C1 and the C6 are very important because it only has one substituent that is not the ring structure with 2 hydrogens. So you can have 2 chair conformations of these 2. So 2 isomers, one is trans, one is cis fused. Okay, so the definition of the cis decoline is that the bridgehead protons, this proton is on the same phase, the trans one on the opposite phase. So what does that mean? So this is cis decoline. Okay, and so let's look at this 6-membrane first. So this bridgehead pointing up axial. So that means it's cis. So this hydrogen also need to pointing up, but it's now equatorial. So this carbon bond is now axial pointing down, and you can draw a 6-membrane from these 2 bonds and draw here, right? So how? Oh, this is wrong. So this is trans. This is a typo. Okay. So this is trans. That means if you put this in axial, so this bond is pointing down axial. All right. And then you can draw 2 6-membrane here. So guess which isomer is less stable? Okay, so actually the less stable decoline isomer is this one because this carbon is in the axial position, right? So if in the axial position, you need to find if there is a 1,3 diaxial interaction. Apparently, this carbon can have interaction with this 3 position, also axial CH bond. But in this one, all these substitutions are in the equatorial, like this carbon bond, this CC bond, CC bond, CC bond. So all the groups on the axial positions are protons. So there is no 1,3 diaxial interactions. So the cis decoline is the less stable. And okay. So if we go to more complex polycyclic structures, for example, if we have testosterone, so we have these 4 rings fused together, okay? And what I want you to figure out and to note is that it has a kind of like a cis-decoline, this is transdecoline. A transdecoline like call, I will change these typos after this class, okay? the trans-acetylene core that is with 2 hydrogens on the axial positions, okay, instead of the less stable cis-acetylene. And I also want you to notice that there is 1,3 diaxial, but it's here with this methyl and this methyl with this hydrogen 1,3 diaxial. And you can also notice that there is also an envelope-shaped cyclopentene structures in it. Okay, so you can see these 4 carbons are on the same plane, and tell the other carbon, so we are comfortable enough, you just get out of here. So this carbon is out of the plane of E that is composed of these 4 carbons. All right. So, okay. So, so the major topics we have covered in chapter 3 is that there are so many typos here. So I promise you I will change them. Okay. So we didn't cover Fischer projection. We covered Newman projections. Okay. We also covered the conformation of acyclic molecules and chair conformations of cyclohexane. And for the learning of chair conformation of cyclohexane, you need to understand the axial equatorial position, ring flip process, and relative stability of substituted cyclohexanes. All right. So you should be able to derive the IUPAC names, which is covered in Professor Chu's video, and you need to there is a nomenclature drill on the Moodle, and you should be able to draw Newman projections, and you should be able to recognize and classify different strings like torsional, angular, or angle string, or steric. Both angular string and the angle string are fine, both correct both correct description. Okay, and you need to draw the chair conformation of any multi-substituted cyclohexane. And when you have the cyclohexane, you need to identify and draw the axial and equatorial bonds, and understand the ring flip process of the 2 chair conformations. And again, the final one is to analyze the relative stability of these conformations by calculation of the energy cost. And again, these data will be provided in the exam, so you don't need to memorize them. All right. So this is the end of chapter 1, 2, 3. And let's have a break of 10 minutes, and we will be back at 11:27. And then we will start chapter 4, which covers the